the lead code problem, lowest common ancestor of a binary search tree. So in this problem, you'll be given a root node and two nodes P and Q. So you need to find the lowest common ancestor for these two nodes P and Q. So when we say lowest common ancestor, so given the values of P and Q are 7 and 9, so 8 is the lowest common ancestor. Similarly here, for example, imagine they gave the input as 0 and 5. So here the 2 will be the most common lowest common ancestor. And sometimes it could be like, so if they ask us what's the lowest common ancestor of 8 and 9, the value will be 8. So 8 is the ancestor of 9, but still that's the lowest common one. So the value can be itself as well. So they have given us a few constraints which are going to help us. One of them is that the nodes P and Q definitely exist in the binary search tree. So this will make it easier. We don't need to confirm the node exists, we can assume it exists. So usually for these kind of problems, I think the way to solve them is using recursion. But this time I'm going to solve it by using a while loop. So the way to solve it is, since it's binary search tree, we know that the tree is balanced. So given a node, all the values greater than the node will be in the right of this node, and all the values smaller will be in the left side. So we can use that to traverse the tree and use that to find the common ancestor. So yeah, I'll show you how you can do it. So first thing we'll do is create a node, tree node, and assign it to root. Oops. Now we'll just create a while loop to traverse down the tree. So the value of P and Q are lesser than the ancestor. Then we know the ancestor should be somewhere on the left side of that node. So we can use that to keep traversing down the tree. So if p.val we're going to do the same condition. If the value of P and Q is greater than ancestor, then we know the lowest common node will be somewhere on the right of the ancestor. So we can use that to traverse it. Else, so here we have a case where the P and Q on either sides of the node. So if that happens, we need to return the value. So we can just say break, and here we just say return ancestor. So yeah, let's try running the solution. So all the three use cases have passed. We'll try submitting it. So for this solution, the time complexity will be O of log n, because at every point we are either moving to the right or the left. So the processing is taking place in logarithmic time. And for memory complexity, we are just creating one tree node to keep track of which is the ancestor. So that's why it's going to be O of 1, so constant space-time complexity.